Let's continue our discussion on direct versus conjugate addition. And I'll have some examples here for us to look at. So let's go with the simplest example of a conjugate addition. So we'll just have pretty much the smallest molecule we can to test this out. And in this case, we're going to use a strong nucleophile, like a Grignard. So we're using the phenyl magnesium bromide. With a Grignard, you need to run this in like a diethyl ether or THF, some kind of ether. And then we'll need an acid workup step. Which is pretty much up to you what acid you want to use. So in this case, since this is a very strong nucleophile, we're more likely to get 1,2 addition or direct addition. So this is going to be our major product. And we'll get some of the, I'm just going to abbreviate that phenyl ring here. We'll get some of this 1,4 addition. Because it's still possible, even if this one is more likely. Now, if instead we change to a little bit weaker nucleophile, using our same substrate here, and let's just go with an alkoxide, and say sodium methoxide. Oh, I don't need an acid workup in this case because I'll just run this in methanol. And this will provide us with the protons that we need for the workup. So now in this case, our major product is the 1,4 addition. And our minor product is the 1,2. Now, in this case, this is the thermodynamic product. This instead, the 1,2, is the kinetic product. Now, why is that? Why would the stronger nucleophiles be attracted to the carbonyl carbon? Well, there's a larger partial positive charge on the carbonyl carbon versus over here. Remember, it has to do a resonance structure for that to happen. It's just more concentrated right here. Also, the electronegative species is right next to it. So this is going to have the largest positive charge. And when we have a reagent that's less stable, and we have a concentrated negative charge on this carbon, it's going to find the biggest positive charge and just attack it. And once it does that, it's irreversible. It's not going to go back to something that's less stable. And having a negative charge on the oxygen is definitely more stable than having the negative charge on a carbon. So once it attacks here, it can't go back. So you end up making more of this product. Now, in contrast, when we're looking at the thermodynamic product, here we have something that's a lot more stable. In fact, this reaction is reversible. Well, let's think about why, right? When we make this product, say right here, right, we've got a negative charge sitting up here on the oxygen. Well, there's a negative charge sitting on that oxygen. And so the intermediate product for having a negative charge here is about as stable as this is. So this can go backwards, back and forth. So something else must cause it to go here rather than there, right? Because this one must be more stable somehow. And indeed, it's quite simple to find out why. This bond right here is about 720 kilojoules per mole. And the double bond here is only about 619 on average kilojoules per mole. So if I break this bond, it's a lot easier than breaking that bond. So this one is the weaker bond, so it's easier to break that one. That one ends up being the thermodynamic product just because it's easier to break. This one's the stronger bond, so this will be lower in energy than this one will. Now, again, the reason why this gets formed is it's under kinetic conditions, and a lot of these really strong carbon nucleophile reactions will happen under kinetic conditions. It's just how that has to happen. So let's just look at what reagents would lead to a reversible situation, or what nucleophiles, and what ones would be irreversible. So reversible, and then irreversible. So reversible ones would be like our hydroxide, and of course the corresponding alkoxide base should be clear that that is an example of a reversible one. Nitrogen nucleophiles, same kind of thing. Any of the halogens like chloride, bromide, iodide, these are really pretty stable ions, so it shouldn't be a surprise that that would lead to a reversible reaction. Carboxylic acids that have been deprotonated, it's quite stable, it has resonance stabilization, so this is a more reversible. We have our cyanide ion, that's pretty stable. And any of those alpha hydrogens that have been deprotonated, right? So if we have a negative charge right here on the carbon, that's not as strong of a nucleophile because it's resonance stabilized, right? Then we come over to things that are irreversible. When it attacks, it's not going to let go. So our Grignard reagents, our organolithium reagents, these are very strong nucleophiles right here. Wittig reagents, those are very strong nucleophiles. So they will attack that oxygen right up here. It's not going to do a 1,4. And then our lithium aluminum hydride and sodium borohydride, those are very strong as well, and they'll add irreversibly. So in these cases, they'll do a direct addition or 1,2 addition. And over here, they'll do Michael addition or 1,4 addition. Preferentially, you'll still get some of both, but you'll get a lot more of the 1,4 if you're in a reversible situation. You'll get much more of the 1,2 in an irreversible situation. And of course, all of this depends on having that conjugation for that double bond. If that doesn't exist, none of this would apply.